Welcome back for a new colloquium. Today's speaker is Ananth Shankar from Northwestern. Ananth got his PhD from Harvard under the supervision of Kizim. Before becoming a faculty at Northwestern, he held a postdoctoral position at MIT, and he was an assistant professor at Madison. And today he's going to talk about the distribution of points on modular spaces.
First of all, thank you. Thank you very much for inviting me to speak here. It's a great honor. Yeah, my title is the distribution of points on moduli spaces. Before talking about what points and what moduli spaces, let me first introduce the most basic objects that are relevant to this question, namely elliptic curves. And I should apologize to anyone who was there at my talk yesterday because it's going to be the same introduction. Nonetheless, a complex elliptic curve is just the quotient of the complex numbers by a rank 2 lattice. Lambda. So a lattice is a discrete free abelian group of rank 2. And because they're quotienting out an abelian group by another abelian group, the result is going to be also an abelian group. And it's going to be compact, and it's going to have the structure of a complex manifold. So it's actually going to be an abelian compact complex Lie group. So this object, an elliptic curve, a priori it looks like a topological space, maybe a complex manifold, but it's actually going to be algebraic. In other words, it's defined by solutions to polynomial equations. You can always find complex numbers a and b, so that you can realize most of this complex terms as the set of solutions to the equation y squared equals x cubed plus ax plus b. So if your goal is to parameterize such objects, then parameterizing complex elliptic curves is the same as asking for the question that if you're given two different lattices, when will the two quotients be isomorphic? So any map of elliptic curves is going to be induced by a complex linear map from C to C. And conversely, a complex linear map from C to C is going to induce a map of elliptic curves precisely when the complex linear map sends the first lattice to the second lattice. And the map is going to be an isomorphism if and only if T of lambda 1 is equal to lambda 2, not just contained in lambda 2. And of course, because C is a one-dimensional complex vector space, any linear map is just going to be scaling by a complex number. And so what we're asking for is when can you find a complex number so that it scales the first lattice to the second lattice? In other words, two elliptic curves will be isomorphic precisely when there's a complex number that scales your first lattice to equal your second lattice. So parameterizing complex elliptic curves is the same as classifying lattices up to complex scaling. So well, how might you go about doing that? Every lattice is a rank 2 abelian group sitting inside C, and so it's going to be generated by two elements. By scaling, you can always assume that one of your elements is 1, one of your basis vectors for lattice is 1, and the other generator, because you want your abelian group to be discrete, if there are to be any complex number that's not real, because if the other element was real, then the group generated by 1 and a real number would not be discrete. Okay. Now, the group generated by 1 and a complex number, tau, is going to be the same as the group generated by 1 and negative tau. So by replacing tau with its negation if necessary, we can assume that the imaginary part of tau is positive. All right, so then we want to know when one lattice of the form 1 comma tau scales to a lattice of the form 1 comma tau prime. And this ends up being a question of just solving linear equations. And solving these linear equations tells you that the lattice 1 comma tau scales to 1 comma tau prime if and only if you can find an integer matrix ABCD with determinant 1 where tau prime equals a tau plus b over c tau plus d. So let's define the upper half plane to be the set of all complex numbers with positive imaginary part. So this is not just a subset of C, it also carries a natural hyperbolic metric. Now you can ask for the group of holomorphic isometries on this upper half plane. And in fact, SL2R acts on H by holomorphic isometries, mainly by fractional linear transformations. Then now your ABCD is not just a matrix with Z coefficients, it's a matrix with R coefficients, and it's the same action. And of course, the complex modular curve is defined to be the quotient of the upper half plane by SL2Z. And this action has a very nice so-called fundamental domain, which was described by Gauss, and that's what it looks like. All right. So as you've seen, the modular space of complex elliptic curves, or in other words, complex elliptic curves themselves, are in bijection with this complex modular curve. Now, just like elliptic curves, which are a priori defined as complex objects, are actually algebraic objects, but the modular curve is also going to be an algebraic curve. It's defined by polynomial equations. Now, we defined elliptic curves. We saw that elliptic curves have algebraic equations of the form y squared equals x cubed plus ax plus b. Well, a and b could be rational numbers, in which case the elliptic curve is like a rational object. A and b could be defined over any field, in which case the elliptic curve will be defined over that field. And similarly, the modular curve, not just is it a complex algebraic curve, it's actually defined by equations over Z. And the modular curve is not just the parameter space of complex elliptic curves, it's the parameter space of elliptic curves over any base. So the data of giving an elliptic curve over any ring is the same as finding a point of your modular curve with entries in that ring. Now, what I'm saying is not quite accurate. There's issues with stacks and stabilizers and such like, which I talked about yesterday. But after these issues, the modular space of elliptic curves is indeed defined over Z, and the modular curve parameterizes elliptic curves over any base. So we've seen that every elliptic curve is an abelian group, and every abelian group admits a bunch of self maps to itself. Namely, you take any point, you fix a number once and for all, let's say 2, and then take a point in your group and multiply that, and then add that point of the group to itself. So that's like 2 times the point. That gives you a map from the group to itself. There's nothing special about 2. You can do this for 3, you can do this for 4. So for any number n, there's a map from an abelian group to itself given by just taking an element and composing it with itself n times. So every elliptic curve has such maps, has such self maps. So a question you can ask is, are there elliptic curves with non-obvious self maps, namely self maps that are not of this form? And what points in your parameter space parameterize such elliptic curves? Now, asking for a non-obvious self map is the same as asking for a self map whose kernel is a cyclic group. So you can just see this by going back to our definition of an elliptic curve as C mod lambda. And that tells you that having a non-obvious self map is the same as having a self map with kernel a cyclic group. Now, let's define a point on the modular curve to be special if the elliptic curve it parameterizes has such an extra endomorphism. And such an elliptic curve is called a CM elliptic curve, CM standing for complex multiplication. Okay. No, you're right. So for the most part, special points are called CN points, but eventually I'll be talking about Shimura varieties that don't parameterize abelian varieties and elliptic curves, and there they call special points. In the sense that I'd want to call them a CN point anyway, but the terminology is special point. So just to make things uniform. All right. So special points on the modular curve are also of interest for completely different reasons. As it turns out, they parameterize integral definite binary quadratic forms, and therefore ideal classes and imaginary quadratic fields. And that's why Gauss was interested in the upper half plane and the action of SL2Z and the fundamental domain, because of precisely this reason. All right. So, well, how are these special points distributed in your moduli space? That's a question that makes sense. Again, it's not very hard to figure out when an elliptic curve has an extra endomorphism just by using the definition of your elliptic curve as C mod lambda. All you need to know is when is there a linear map from C to itself that sends a lattice to itself. That again ends up being a question of solving linear equations. And it turns out that a point is special if and only if the associated point in the upper half plane satisfies the quadratic equation with integer coefficients. And to insist that it has to be non-zero coefficient, let's just insist that the coefficients are all co-prime integers. So associated to such a point is an invariant called its discriminant, which we define as negative d equals b squared minus 4ac. As it turns out, there are, and I think this is due to Brouwer and Ziegel, there are approximately b to the half plus or minus up to an error special points having discriminant negative d. So let's call the set of all special points with the same discriminant, let's call it lambda d. It's a subset of the modular curve. Now, how does the subset distribute in A1? And it's a really beautiful theorem of Duke that tells you that as your d goes to infinity, any sequence of d going to infinity, this set equidistributes to the hyperbolic measure in the modular curve. It's extremely easy to see that this set must be dense in the modular curve, namely fills it out, but Duke actually proves an equidistribution result, which is much, much, much stronger. So I think now might be a time for me to pause for questions if there's any.
So the number of special point is the class number, or
Yeah, exactly. That's exactly right. Yeah,
the
yeah.
L function is the plus or minus epsilon.
The class number has
The L function is the plus or minus epsilon. You know, there's a square root of d and then it's a class number.
it's a class number. It's a class number. Yeah. So so this is the most basic moduli space that's going to show up, and now let me start talking about more general moduli spaces, such as Shimura varieties. So the modular curve is the most basic example of a Shimura variety. The upper half plane was like a crucial player in defining the modular curve. A generalization of the upper half plane are objects called Hermitian symmetric domains. These are again bounded spaces which have a Hermitian metric, a negatively curved metric. Now, the group SL2R was acted on H by holomorphic isometries. And similarly, if you were to look at the group of holomorphic isometries on a Hermitian symmetric domain, that's going to be a real Lie group. We define the modular curve by picking a discrete subgroup of SL2R, namely SL2Z. The analog in the setting of Shimura varieties is going to be an arithmetic subgroup of the group of holomorphic isometries. And just as we define the modular curve to be H mod SL2Z, your Shimura variety is defined to be X mod gamma, where gamma is an arithmetic subgroup. Now, just as your modular curve, which a priori looks like a complex space, is actually algebraic, so is your Shimura variety. Just like your modular curve was defined over Z, your Shimura variety is also going to be defined by equations, by polynomial equations with coefficients in an explicitly defined number field. And in fact, there's a rich theory of integral models that tell you that for the most part, these equations are also going to be integral. So your Shimura varieties are, loosely speaking, defined over rings of integers, which are just generalizations of the set of integers. Now, just like points of your modular curve parameterize elliptic curves, points of your Shimura varieties parameterize Hod structures. And so your Shimura variety carries a variation of Hod structures. An elliptic curve, a special point, is a point that parameterizes a special sort of elliptic curve, namely a CM elliptic curve. And the generalization in the setting of Shimura varieties are Hod structures where the Mumford-Tate group is commutative. This works out to be exactly the same as in the setting of elliptic curves as your elliptic curve being Cn. So let's perhaps look at a few examples of Shimura varieties. Now, elliptic curve generalizations of them are abelian varieties, and the parameter space are also Shimura varieties. Just like the group SL2 and GL2 defines your modular curve, symplectic groups define the moduli space of abelian varieties. And special points are going to parameterize CM abelian varieties, namely abelian varieties with lots and lots of extra endomorphisms, where lots and lots is a very quantifiable and technical, has a very quantifiable and technical definition. If you were to look at orthogonal groups, where the signature is 2, n, then these orthogonal groups parameterize K3 surfaces, which are also objects of arithmetic and geometric interest. There's many Shimura varieties. There are Shimura varieties not known to parameterized geometric objects. These are associated to exceptional Lie groups, which I briefly hinted on yesterday, and also certain orthogonal groups.
But are you supposed they're not known? What is it, a conjecture that they would all parameterize algebraic object or no?
I think people expect them to, but have no idea where to look for them, where to look for the geometric objects. There's lots of conjectures about whenever you're given local systems or cohomological data of a certain type over varieties, then these local systems and cohomological data should arise as a cohomology of a family of geometric objects.
Okay.
And certainly the local systems on exceptional Shimura varieties satisfy the hypotheses of these conjectures. It's just that we don't know where to find them. Special points are also yes.
So in the case where we do know that it does parameterize geometric objects, is there some sense which we can say like there's a canonical choice of geometric objects that they're parameterizing, or can the same family parameterize many different kinds of families of geometric objects?
More or less canonical choice of geometric objects, and usually and there are abelian varieties. Like you put the only Shimura varieties that parameterize the geometric objects are the ones that map to AG. So these you do have moduli of polarized K3 surfaces, but then the Kuber hierarchy construction also gives you a family of abelian varieties on these orthogonal Shimura varieties. So pretty much everything, the only thing that we know are abelian varieties and things intimately linked to them, namely K3 surfaces. Back to the question. So special points are also Shimura varieties in their own right, and they're zero-dimensional Shimura varieties. They are just like your modular curve is associated to SL2 and GL2, and your moduli space of abelian varieties is associated to a symplectic group and to the group of symplectic similitudes. Similarly, special points are associated to tori, to tori defined over Q, toric groups. And they're all defined over Q bar, and in fact, they're all defined over fairly explicitly defined number fields. Shimura varieties also map to each other, and all these maps are dictated by group theory. So for instance, the modular curve is A1, and the parameter space of abelian surfaces is A2. So given a point in A1, is there a natural way to associate to it a point in A2? In fact, yes, there is, because a point in A1 is going to correspond to an elliptic curve. Given an elliptic curve, is there a natural way to associate to it an abelian surface? Yes, there is. Just take the product of the elliptic curve by itself. So that gives you an assignment from the modular curve to the moduli space of abelian surfaces. And in fact, so this is a map of Shimura varieties. Similarly, given a pair of elliptic curves, you also get an abelian surface. And this is captured by looking by the fact that there's a map from A1 cross A1 to A2. And under these maps of Shimura varieties, special points always map to special points. So Shimura varieties are interesting not just in their own right, but they also can be used to prove a bunch of arithmetic theorems. So for instance, by studying the modular curve and special points on the modular curve, Elkies proved his landmark theorem, namely that if you have an elliptic curve defined over the rational numbers, then it has infinitely many super-singular primes. So this is a question that that was thought to be extremely difficult, and Elkies just came up with a really beautiful argument and proved that if you take any elliptic curve over rational number, over the rational numbers, then you can reduce its coefficients modulo primes for all but finitely many primes. So then you get elliptic curves and positive characteristic. You can ask whether these elliptic curves you get are ordinary or not ordinary. And it was known that at most primes you will be ordinary, but it was also expected that there's infinitely many primes modulo which are not ordinary, but it was known that this small set was infinite until Elkies proved his landmark theorem, and he did this by studying the modular curve and special points on the modular curve. Now, similarly, Francois Charles studied intersection theory on the modular curve and proved the following striking result. Namely, if you have any two elliptic curves defined over a number field, and especially those that don't map to each other, they will map to each other mod P for infinitely many primes P. And again, like in the case of elliptic curves, again, like in the case of super-singular primes, it's known that the set of P modulo which E1 maps to E2 is a thin set. So just like Elkies, Francois also proved that this thin set of primes is actually infinite. And along similar lines, in joint work with Ananth Shankar, Yunqing Tang, and Salim Tayu, we proved that if you have an abelian surface defined over a number field with potentially good reduction everywhere, then there's infinitely many primes, modulo which it maps to a product of elliptic curves. And this is also a situation where we prove that a thin set of primes is actually infinite.
What do you mean by E1 maps to E2 by P?
Isogenous. I just mean isogenous.
Oh, there's an isogeny between E1 and E2 by P.
Exactly.
And of course, there's no global isogeny.
Exactly right. Now we are saying it is the AP values are the same.
Oh, that's what you're saying.
Yes, that's what I'm saying.
The
The AP values are same for infinitely many primes P.
Oh,
Absolutely. And perhaps you expect this. And perhaps you expect this because the range of AP values is around square root P, 2 square root P, and so the probability is 1 over square root P, give or take. And so you would expect infinitely many primes. Absolutely, absolutely.
and is it, I'm sorry, is it similar to Elki's proof? Is it a similar argument or?
Yes, it's inspired in some. It's like yes, it's definitely inspired by Elki's proof. So Elki's shows like demonstrates congruences between a non-special point and special points. He sort of he cleverly constructs CM points and constructs and shows congruences, and thereby deduces super-singularity. And Francois also pretty much works with congruences. So he starts off with an elliptic curve and he moves it around by Hecke, and he shows that as you sort of take Hecke translates of this fixed point E1, and you fix E2, then you have more and more congruences at more and more primes P. It's a similar enough argument to Elkies, absolutely. Yes.
Is there any idea about the density of each prime?
That's a great question. So if density is 0, definitely density is 0, so that's known. You expect x to the half up to log, so let's say plus minus epsilon. But I think
Elki's proof gives you log x.
exactly, and I don't think Francois' proof is going to do any better than log x. So, and I don't know if anyone has actually done this, but it's unlikely that anything better than log x will work.
You're actually proving that it's super-singular modulo infinitely many times.
Who are us? No, not at all, not at all. We only prove isogenous to a product of elliptic curves. Non-simple. Even if I'm not even sure whether to expect infinitely many primes of super-singularity or not in the setting of abelian surfaces. But even if you do, but at the very best, it'll be the probability at the very best will be something like 1 over P.
What would be 1 over?
The probability that mod P super-singular will be at the very best. So you'd expect it to be 1 over P squared because the super-singular locus is codimension 2. But then because of the reducible components, you have more points mod P than you have more points over FP than perhaps you'd expect otherwise. And I think you have enough points so that the probability becomes 1 over P. But none of this is at all translatable into a proof. And you're not going to see this in data either, because at least over here you'll see lots of at least if your probability is 1 over root P, if you were to actually look at data, you will see lots and you will see enough primes, not lots and lots, but you'll see enough primes which are super-singular. But if this is a probability, then you're not going to see anything in the data. Thanks very much for the question. And all this we do by studying low-dimensional orthogonal Shimura varieties. And we're also able to push Francois' program to its logical conclusion by studying high-dimensional orthogonal Shimura varieties as well. And the geometric theorem that we prove is that if you have a K3 surface defined over a number field, then it requires an extra line bundle, mod P, at infinitely many primes P. And in all these cases, we are we're like showing that there's lots and lots. Well, we're showing that there's infinitely many primes in a thin set, in a density 0 set. All right. So let me get back to the title of my talk, namely special points in moduli spaces. So we saw that Duke proved a really beautiful and strong equidistribution theorem for special points on the modular curve. Now, asking for such analytic equidistribution theorems for special points and high-dimensional Shimura varieties seems to be completely out of reach. It's a very hard question, and there's really beautiful work of Ilya Khayutin where he makes partial progress in the setting of a product of two modular curves, and even that's a very significant advance. But there's nothing beyond Ilya's work in high dimensions as far as analytic equidistribution is concerned. So an easier question to ask, well, to answer at least, is the question of the algebraic distribution of special points. So it's well known, and it's not difficult to show, that special points are Zariski dense, algebraically dense in the Shimura variety. And in fact, it's even easy to show that your special points are holomorphically dense in your Shimura variety. Just like the set of all complex numbers which, say, lie in an imaginary quadratic field are dense in the set of complex numbers. It's a very similar picture. But if we want to understand the algebraic distribution of special points in the Shimura variety, then the natural question to ask is, when does a subvariety of a Shimura variety have a Zariski dense set of special points? Now, given that special points are dense in the whole Shimura variety, well, S itself is a subvariety that has a Zariski dense set of special points. We've seen that Shimura varieties map to each other, and under these maps, special points map to each other. So the image of any Shimura variety is also going to have a Zariski dense set of special points. And you can slightly generalize this to say that Shimura subvarieties of S also have a Zariski dense set of special points. And the question is, are there any others? And the conjecture of Andre-Oort posits that if you have any subvariety that has a dense set of special points, then that subvariety has to be a Shimura subvariety of your ambient Shimura variety. Namely, the only ones that have a Zariski dense set of special points are the obvious ones. So here's an example of this conjecture in action. So if you were to consider the modular curve, then this doesn't really say anything, because any subvariety is either going to be the whole curve or it's going to be a finite set of points. Nothing very exciting about it. But as soon as you will look at a product of two modular curves, then you can start asking very interesting questions. Namely, if you have an irreducible curve that contains a dense set of special points, well, then is there a nice description of this curve? The Andre-Oort conjecture predicts that either your curve is going to be a point cross the second axis, or the first axis cross a point, where in either case the point is a special point. So these are special, and these clearly have a dense set of special points because A1 has a dense set of special points, it being a Shimura variety. Slightly more, quite a bit more exciting are so-called modular curves that fit inside A1 cross A1. So you could look at the sublocus in A1 cross A1 consisting of points, consisting of pairs of elliptic curves which admit a map, so that there's a map from one to the other, where the kernel is a cyclic subgroup of size n. Let's call that locus y0 of n. Well, what the Andre-Oort conjecture predicts is either your C is going to be one of these Bowen curves, x plus a1 or a1 plus x, or it's going to be y0 of n. So as soon as it passes through infinitely many special points, it's extremely constrained. And conditional on the Riemann hypothesis, Adic proves this beautiful theorem, and Andre proves this theorem without any conditionality on the Riemann hypothesis. So a lot of people have done a huge amount of work on this conjecture. So here's an extremely non-exhaustive list of past work. So Adic proves that the Andre-Oort conjecture is true for arbitrary products of the modular curve, conditional on the Riemann hypothesis. Then again, conditional on the Riemann hypothesis, Klingler and Yaffe prove the Andre-Oort conjecture for all Shimura varieties. Then Jacob Zimmerman proved the Andre-Oort conjecture for AG, and I think this is one of this was one of the biggest advances on this conjecture. And proving it for AG formally proves it for every Shimura subvariety of AG. It proves it for pretty much every Shimura variety of abelian type, namely any Shimura variety associated to a symplectic group or to a linear group and to most orthogonal groups. So the only groups that are left over are some orthogonal groups and some exceptional groups. And in joint work with Zimmerman, with Thiel and Zimmerman, as well as an appendix with Elaine Eno and Groznik, we prove the Andre-Oort conjecture for these leftover Shimura varieties, and therefore that establishes the conjecture for all Shimura varieties. So that's, I think, what I want to say about the algebraic distribution of special points. So if time permits, I'll come back at the end to give a brief sketch of how this is proved.
Yeah, just gonna ask. The Andre-Oort conjecture is for a curve which contains a dense set of CM points.
It's for any variety that contains a Zalski dense set of, it's any subvariety that contains a dense set of CM points.
Any subvariety.
Any subvariety, yes.
Will that be different, you know?
Yeah, so you could just, okay, so take the Zalski closure. If there happens to be whatever that Zalski closure is, that will be a Shimura subvariety. So if this infinite set that you have happens to pass through a single curve, then that curve will be Shimura curve. So you could take any subvariety containing the Shimura curve, and so it will automatically contain all these special points. So another way of stating the conjecture is to say that you take any set of special points, take the Zalski closure, that should be a Shimura subvariety.
Yeah, that's a better way to get.
Yeah, no, absolutely, for sure.
No, I mean that's what I mean. Now I understand.
Right. Absolutely, thank you. So, well, we briefly talked about the complex distribution of special points, and we saw that Duke had a really beautiful theorem. Now talked about the algebraic distribution of special points, and the Andre-Oort conjecture tells you what to expect. Now, I now want to talk about the P-adic distribution of special points, and also briefly touch upon what it means for a point mod P to be special. So, well, I said P-adic. So, what are the P-adic numbers? Apart from the Archimedean metric, the rational numbers have a bunch of other metrics. If you were to take a prime, any prime number P, then we just decree the P-adic size of an integer to be small if that integer is divisible by a large power of P. So for instance, if you take P equals 2, then 64 is very small. 1 over 64 is very large. So you can make this precise by taking a rational number, and given a rational number, you can write it as some power of P, either positive or negative, multiplied by A over B, where neither A nor B are divisible by P. So we have your rational number is of the form P is the alpha multiplied by A over B, and P doesn't divide either A or B. So then this number alpha is uniquely defined. So given this setting, the P-adic size of this number is defined to be 1 over P is the alpha. So if your rational number has a large denominator, has a large power of P dividing the denominator, then its size is large. If it has a large power of P dividing the numerator, then the size is small.
You mean P does not divide?
P does not divide. Thank you. Yes, indeed. And as it turns out, these are the only metrics you can put on the rational numbers, namely the usual one as well as these ones as you vary across different primes P. So, well, what you do when given a field and a metric, you complete it. And the completion is called, we define the completion to be QP, or rather we call the completion QP. And just like the set of real numbers in the field, QP is also a field, and it also it contains Q as a dense subset. Given any algebraic variety over Q, you can think of it as an algebraic variety over QP. And its QP bar points of this algebraic variety will have a topology coming from the P-adic metric, just like the real valued points of a variety has the Archimedean topology. The complex valued points of a variety has the Archimedean topology as well. Same happens for the P-adic topology and the P-adic metric. So how does points get distributed in OG under the P-adic metric? So let me perhaps write something on the board. Let's perhaps take the case of the modular space of abelian surfaces. So like I said, this Shimura variety is actually defined by integer coefficients, and so you can reduce the coefficients mod P for any prime P. Now, let's look at the QP bar valued points of this moduli space, and let's look at the SP bar valued points of the moduli space. Now, loosely speaking, given any point that's a QP bar valued point, you can reduce it mod P to get a point, to get an SP bar valued point. Just like any number can be reduced mod P, you can do the same for points and varieties. So here is something that looks like an open unit disk. So take any point mod P and then look at the locus of all points in over QP bar that reduce to this point mod P. So this should be thought of as an open unit disk. Similarly, you can take any locus inside here, say a curve, and you can look at the locus of all points that reduce to this curve mod P. So first approximation way of thinking about the locus of all points reducing to say a curve mod P is just going to be you have a bunch of open balls indexed by points on this curve, and they like all fit together to form some sort of a swath to form a P-adic swath of the space. So if you want to understand the P-adic distribution of points on the space, then there's two things you need to understand. You need to understand how the points get distributed mod P. And then within each point mod P, you sort of also want to understand how they get distributed in this unit ball thing of points that reduce to this specific point mod P. So loosely speaking, you need to first of all understand how things work mod P. And then for every fixed point mod P, you want to figure out how things work within this ball. At least that gives you a first order understanding of how things work. So how do special points, what points mod P are special? In this specific setting, that's the same as asking for when an abelian variety over SP bar is a CM abelian variety. And what Tate proves is it always is. So every abelian variety over SP bar is actually going to be CM. So every point over SP bar is special. Extremely different from characteristic 0, where, well, special points are like countable and your space is uncountable. So things are different already. Now, when a Shimura variety does not parameterize abelian varieties, well, then how do you even define the notion of a special point mod P? In characteristic 0, we had a Hecke definition. Yeah, yes, please.
It's true, it's Frobenius.
Yes.
Is it the same thing? Same thing in there? It's
Well,
Frobenius, which is the special point. So is that what you mean?
So Frobenius by itself isn't going to generate your CM field. Just like this again, the case of elliptic curves, your Frobenius generates your endomorphisms only in the ordinary case. The super-singular case, Frobenius is scaling. But the point is, your endomorphisms are the commutant of Galois, and to the commutant of one specific element. And that element is semi-simple. So that gives you lots of endomorphisms.
It's not as simple as the case of elliptic.
Not quite, but Tate proves it really beautifully in his paper on
And therefore,
the Tate conjecture. This is Frobenius. This is absolutely Frobenius, and your endomorphisms will be the commutant of that Frobenius, interpreted suitably. So we define special points in characteristic 0 outside the abelian case to be points parameterizing Mumford-Tate groups, which are commutative. Well, now I've used this word Mumford-Tate group without telling you what it is, but it's associated with something called a Hodge structure. And a Hodge structure is a transcendental object that requires you to be working over the complex numbers. Well, you can't do this over here. So how do you define the notion of a special point in general? So as it turns out, you can define a special point to be a point that's fixed by lots and lots of Hecke correspondences. That definition is equivalent to the case of CM in the setting of abelian Shimura varieties, and in joint work with Zimmerman and with Baker and Zimmerman, Ben Baker and Zimmerman, we prove that if you have an exceptional Shimura variety, then for large enough times P, every mod P point is special. In other words, every mod P point is going to be fixed by sufficiently many Hecke operators. So mod P, everything is going to be special. Well, now what's going to be the P-adic distribution of these special points? So pick a point mod P, look at the locus of all points reducing to that point mod P, look at the sublocus consisting of special points. What sort of sublocus should you expect? So, and abelian variety is defined to be ordinary if it has more p torsion, if it has like sufficiently many p torsions. In particular, if the p torsion subgroup of your of the points of the FP bar valued points of abelian variety is z mod pz to the g. So as it turns out, this condition of an abelian variety being ordinary is a generic condition. Namely, most abelian varieties will be ordinary. The locus of points consisting of ordinary abelian varieties is like going to be some open. Now, extremely beautiful work of Ser and Tate tell you exactly what the set of all Cn points reducing to an ordinary point is. Now, in the complex topology, your Cn points are dense. In the P-adic topology, in this specific case, your Cn points are going to be discrete. They're going to be P-adically discrete. In fact, this disk is going to look like some sort of a torus, and your Cn points will be torsion points of this torus. And even though the answer is quite different from the complex case, you have a full and complete description. You have a bunch of, every ordinary point has a CM lift. There's a distinguished CM lift because, well, the set of torsion points have a distinguished element, namely the identity. And these torsion points are extremely well spaced out and very well understood. So the ordinary case is easy to understand. Now the opposite end of ordinary is super-singular. In the setting of elliptic curves, there's ordinary and super-singular and nothing in between. As you look at high dimensions, there's a lot of stuff in between, but ordinary is one end and super-singular is the other end. I'm not going to talk about anything in between. Now, in the case of elliptic curves, you only have finitely many super-singular elliptic curves. But as soon as the dimension is larger, your moduli space of super-singular abelian varieties is going to be positive dimensional. It's loosely speaking going to be, I think it's going to be the floor of g squared over 4.
Inside the space of which define dimension.
Inside the space of dimension g times g plus 1 over 2.
Thank you.
In particular, in the case of A2, you're going to have a curve. So we have A2, we have the super-singular locus, that's a curve, and we have the set of all points that reduce to the super-singular locus, not P. All right. Now, in the case of elliptic curves, every super-singular elliptic curve has a lift to a special point. Namely, given any super-singular elliptic curve, there is going to be an elliptic curve in characteristic 0 that has Cn that reduces to a super-singular elliptic curve, mod P. Now, as it turns out, this is not true once G is at least 2. So, building on work of Oort, Chai, Conrad, and Oort prove that there are super-singular points in AG that don't admit lifts to special points. But there are some super-singular points that do admit lifts to special points. So, natural question to ask is, well, are there more CM points that lift? Are there more super-singular points that have CM lifts? Or are there more super-singular points that don't have CM lifts? And in joint work with Kisan, Josh Lamb, and Padma Srinivasan, we proved that only finitely many super-singular abelian varieties admit CM lifts to characteristic 0. So you should have quite a few CM points over here, but they're all clustered in finitely many, and most of the space, most of the set of all points that have super-singular reduction most of the space does not contain any CM points at all. So this is diametrically opposite to the case of ordinary points. And we also prove that only finitely many K3 super-singular K3 surfaces admit lift to CM K3 surfaces once P is at least 5. We expect the same to be true for P equals 2 and 3, but as soon as P is 5, then at least 5, then only finitely many super-singular K3s admit CM lifts. And what happens when you're neither ordinary nor super-singular? Well, we have precise theorems there as well, but then stating them requires too much setup, so I won't say anything there. All right. So something that's intimately related to CM points are so-called Hecke orbits and Hecke correspondences. And in fact, you can even realize CM points as fixed points of these Hecke correspondences. These are multi-valued functions from the Shimura variety to itself. These Hecke correspondences are algebraic and they can be reduced mod P. And the Archimedean behavior of these Hecke correspondences is well understood. It's a beautiful theorem of Clauzel, O, and Ulmo, who proved that if you start off with a point and you hit it with more and more Hecke operators, then the resulting sequence sets that you get again equidistribute in the hyperbolic metric to your in your Shimura variety. So they prove Duke's theorem except for Hecke orbits, and they do it for pretty much all Shimura varieties, not just for the modular curve. All right. What about the P-adic and not P distribution of Hecke orbits? Now, as it turns out, the notion of whether you're ordinary or not, and the notion of whether you're super singular or not, all of this is less invariant under Hecke translations. So if you take a super singular point, and if you were to move it around by Hecke however much you wanted, you would stay in this locus, you would not leave this locus, you can't be dense at all. And the only hope you have of density is if you start off with an ordinary point, namely a point that's in this generic stratum. And I note conjecture that in such a setting, the Hecke orbit of your point should be Zariski dense. And in a really beautiful paper in the 90s, Chai proves this for AG. And he also proves this for Hilbert modular varieties, which are like moduli spaces of abelian varieties with certain types of extra endomorphisms. So in joint work with Yunxing Tang and Devesh Malik, we prove new cases of the ordinary Hecke orbit conjecture. In particular, I show that the Hecke orbit conjecture, the ordinary Hecke orbit conjecture, is true for any Shimura variety associated to a twist of a symplectic group. And in joint work with Devesh Malik and Yunxing, we prove that the ordinary Hecke orbit conjecture is true for orthogonal Shimura varieties, specifically Shimura varieties associated with groups of the form SO2, N, as well as unitary U1N Shimura varieties. And this is very related to our theorem on Picard ranks of K3 surfaces. And in a future work, and later, using the parabolicity conjecture proved by Marco di Adesio, they prove the Hecke orbit conjecture is true for Shimura varieties of abelian type. So this is a really interesting result. And they also address the case of non-ordinary loci, where once you define things correctly, there's a proper conjecture to be made. So, well, this is the mod P distribution of Hecke correspondences and Hecke operators. What about the P-adic distribution? So, if you were to take a point in characteristic 0, and if you were to take the Hecke orbit, it's sort of going to be like a somewhat discrete set in the sense that if you fix a Hecke operator and apply to a point, you're going to get a finite union of points. You're going to get a finite number of points, and then you take the union over, you take the countable union over countably many Hecke operators, and that's known to be dense. But either way, you're just taking a union of finitely many points defined over larger and larger fields. Now, prime to P Hecke operators behave very similarly, at least in this sense, mod P, but P power Hecke operators behave differently. If you will take the P power Hecke operator of an ordinary point, well, that does behave like in characteristic 0. But if you were to fix if you will take an appropriate P power Hecke operator and apply it to a super singular point, you end up getting a positive dimensional variety, namely the whole super singular locus itself. So unlike in characteristic 0, the Hecke image of a point can actually be a positive dimensional subvariety if you work with P power Hecke correspondences. Well, all right, so you start off with a point in characteristic 0, move it around by Hecke, you sort of get a somewhat discrete set. You reduce that point mod P, you move it around by Hecke, you can get a positive dimensional subvariety. What happens if you take the Hecke orbit in characteristic 0, reduce it mod P, and see what subset you get? So we show that it's actually going to be finite. So you take any point with super singular reduction, so take any point in the SWOD defined over a finite expression of QP, take the entire Hecke orbit, reduce it mod P, you get a finite subset of this positive dimensional space. Whereas if you were to take this point, reduce it mod p, then take the Hecke orbit, you get the whole subvariety. So this should be thought of as like a companion problem to the CM lifting problem, because every point in this positive dimensional subvariety CM is CM, but you only see finitely many of them as reductions of CM points. And we also have analogous but somewhat weaker results in the setting where you're neither ordinary nor super singular, but again, that's going to take too much setup to define. All right, so there's 4 minutes left. I can either go over time or I can stop now. So let me stop now. Thanks very much for your attention.
Thank you very much for the beautiful talk. And so, questions?
I was trying to understand what you said at the very end. So when you take the Hecke orbit of A, that's under all Hecke operators?
All Hecke operators, yes.
So including at P.
Exactly.
But didn't you say that mod P you would get something which is
Positive dimensional.
so how can it be a finite set of a billion varieties? I don't understand how the two things reconcile.
So there's 2 things you can do. You can do B equals you can
That's anticipating the question that I have.
you can either look at P of A mod P, or you can do union of P of A mod P.
What's the difference between the two?
See, start off with an abelian variety in classic 0.
Yeah,
Take everything isogynous to it. You get some number of abelian varieties. That is a mod P.
yeah.
Now you take your abelian variety, reduce it mod P, look at everything isogynous to it. So what I'm telling you is most isogynous don't lift.
No,
Many parts.
I think that the problem is
Uh-huh.
that you're not telling us what you think is T mod P. That your definition of T mod P is not the reduction of the Hecke correspondence from characteristic 0. It's a
You're
different thing.
Correct. So
it's a bit.
so there are you can define it as, so you have a G over here, and you have your Hecke variety. Let's call it H, and then you have AG over here, and this is defined in characteristic 0. And one way to define P of A mod P is to just take the closure of this in the integral model. So this is set AG cross AG. This is a priori defined over QP, but you can just take the closure over ZP. And then you can just take a point and now have a well-defined correspondence over ZP, take the special fiber, take a point, take the inverse image, push it back. And now it's going to be a flat, no, now it's going to be a correspondence that's no longer finite. Here's perhaps a better way of saying this. Let A be defined over QP, and then define isog of A to be the set of all abelian varieties over QP bar, such that B is isogynous to A base change to QP bar.
Isogynous anywhere. But not over.
Anywhere,
Over
anywhere,
QP bar.
over QP bar. Now you can also look at isog of A mod P. This is set of all B over FP bar, such that, well, let's say B bar over FP bar, such that B bar is isogynous to A mod P. This is what I mean by P of A mod P. So take this, reduce it mod P. So you have isog of A mod P sits inside isog of A mod P. This is positive dimensional. This is sort of like some sort of a haphazard random set. Well, but then when you reduce this set mod P, what sort of structure do you get inside this positive dimensional variety? And we prove you get a finite set of points.
So when you reduce the top mod P, you get a finite number of point down. That's what you're saying.
Exactly.
Yeah, because most things mod P, they don't come from something up. They just exist because they exist mod P.
Correct. Exactly right. If you were to, if instead you were ordinary, then every orthogonal mod P lifts to characteristic 0. but it doesn't in a super singular case and in a very strong sense. Does this answer your question?
Yeah.
Okay.
I understand. Thank you.
So, quick question, for certain groups, like we're talking about groups that are not of symmetry to N,
Yes.
where there are no Shimura varieties, but there are still symmetric spaces. So,
Yes.
are there any questions analogous to Andre-Oort we still formulate? I mean, maybe your techniques would not apply, but it can at least make sense of the.
I'm not sure. I should say I'm just starting to learn about. I'm just starting to sort of read your papers with Jan and with Mike and Leonard, and I first need to understand your work before. Yeah. See, I'm not sure.
But I was thinking about also these earlier works of Duke, where he proves not just equidistribution of CM points, but geodesic balls and so on, and whether there would be so those geodesic cycles, of course, are not special points, but they're special things.
Right.
And the statement doesn't require any algebraic geometry.
Right. It's sort of related to real quadratic fields, right? Yeah. I'm not sure. It seems very likely that there should be some sort of theory, but I really don't know what one should expect.
I have a question about the pickup the K3 surfaces.
Yes.
Why is it special, meaning having an extra line bundle? You were saying, when you were doing the example, and then you say there are infinitely many x that gain extra line bundle.
Yes.
So how does this relate in terms of this Manfred? What is this still? I could not see exactly why the line bundle was giving me extra amount.
No, that's right. That's a great question. So if you were to work in A2, and if you were to ask for an abelian surface to split as a product of elliptic curves mod P, that means you have a point in A2, but X mod P lies in A1 cross A1. Now, look at the modular Q3s. Asking for extra line bundles means that you lie in a Shimura subvariety. So if your modular Q3 was something like SO2, 19, then let's say SO2, 18, because the statement is obvious as it turns out SO2, 19. Asking for a K3 over here to have an extra line bundle mod P, you're asking for the point to lie in a sub-Shimura variety corresponding to a smaller group. So you have this point that doesn't lie in a smaller Shimura variety, but what we're saying is that it lies in a smaller Shimura variety mod P for infinitely many primes P.